Good morning, Connie. Are you
Yeah.
there?
Hi, Uso. I'm here.
Yeah, good morning. Thank you for your service. So yeah, everything went well. I mean, last session. So just make sure that this recording is in progress all the time. And if someone asks questions through this Zoom chat or Q&A and the speaker does not see it, then please help him to get this question.
Right.
Yeah. Other than this, it's pretty, straightforward. So you can just make sure everything is up and running.
Yeah.
That's it. Thank you.
So when I start this meeting, the recording just automatically starts. So
Yes.
I assume that it will not load to the cloud, right? It,
Yeah, it will be automatically stored in the cloud, so you don't have to do anything about uploading.
right. Yeah.
Yeah, right after this session, it will take some time to process it, like a few minutes, and sometimes it just takes like a few hours, but eventually it will be automatically populated in the website. So don't worry about it.
Right.
Just make sure that this, you know, recording is always, blinking.
Yeah.
Yeah. I mean, oh, and you actually have two different speakers. So let me quickly check our website. No, I have to check. Oh, I think Professor Lee is already here. Good morning, Professor Lee. Can you hear me?
No, but I'm muted. Now maybe you can hear me.
I can see you and I can hear you clear.
Very good.
Yeah, thank you. Thank you so much for your contribution. So,
Okay.
are you in California right now?
No, I'm in Spain.
Oh, I see. Must be afternoon there, right?
It must be what?
Afternoon.
Yes,
Yeah.
it's in the afternoon. And here's Martin. Martin is in California.
Right.
Hello. Hello, good morning. So, yeah, I think you can see this ESIC logo from participant, right?
Mm-hmm.
He's our volunteer student. His name is Kani. He will be here for the entire session to offer you some help. So basically, I enabled this automatic recording in the cloud. So this will be automatically recorded. And as soon as it is processed, I will send you the files. So
Okay, good.
Connie, can you make Professor Lee and Dr. Lostro co-host?
Yeah, I already made them go.
Oh, okay.
Yeah.
Yeah, I can see that it's already recording as well. One thing I would like to try is see if I can share my screen.
Oh, can you go ahead?
With that in the past, so is that working?
Yeah, I think something is showing up.
Okay.
Yes.
Yeah.
It's showing.
Great.
Mhm.
In the sometimes when I try to stop sharing, my Zoom freezes up. So perhaps I should keep it this way.
Mhm.
Um,
Can you repeat your question again? I was looking at another.
Oh, sometimes when I stop screen sharing, my Zoom freezes up, and then I have to log in.
Oh,
I'm the first
got
one. I'm the first one to start speaking, I guess. Or
well, maybe it would be better.
it works.
Okay, good. Yeah, I was gonna suggest that maybe it would be better to just bite the bullet and reset it now so that we can do the introduction. So I guess I will maybe start by introducing myself and then introduce you, Martin, and turn it over to you for the first part.
Okay. Yeah. Sounds good.
And
Josh, did you see my email about the short bio?
I can handle putting into the chat links as appropriate for things that you're referring to.
Okay. I quickly updated also little screenshot of the paper. I was referring to the archive paper, but of course we have this MSOS paper that would be better to refer to.
Professor Lee, I have to leave to another room, but let me just add one thing. So usually we don't have a big audience in this education class because people know that this video will be available through YouTube later on. So many people decide to watch this asynchronously. So if not many people show up, then I would suggest to start sharp the time, but you can give them more minute to get in. But I mean, I just want to let you know about this. And as soon as this session is over, then I will download all the files and I will share it with you. Okay? And I will be here around, but if something comes up, this our volunteer student here to help you. And just let me know when you need help.
Okay, sounds great.
Great. Thank you. See you around.
All right, bye-bye.
I'm just taking time to clean up my desktop a little bit.
Yeah, I'm doing the same, getting out of a lot of irrelevant apps. Yeah, I guess hopefully if we don't get many participants, at least we get hopefully a nice recording that we can then maybe chop up and use.
Yep, that would be nice.
So you can't have gotten a whole lot of sleep last night because I was getting email from you just a few hours ago.
That's right. That's pretty early.
Mhm.
Just making sure that the diagrams are working, which they are. How are things in Spain?
Things are good. It's been a pretty interesting conference. It's been sort of a crash course for me in how to talk about our field in Spanish.
Yeah, seems hard.
Yeah. So I've actually been learning a lot. It's been kind of fun from that perspective because, I've just never had any serious discussions about what I do in Spanish, what I do professionally. So
Are there some funny words to account for? Like in French, people call a computer ordinateur.
there are quite a few terms that were a little bit surprising to me. One that really sticks in my mind is that Herb Simon's bounded rationality translates as racionalidad acotada, which when they first told me that, I thought I heard it as racionalidad agotada, which means exhausted rationality.
That's funny.
Yeah.
It's funny to get up so early for a meeting that most people will attend at their own time.
Yeah. I do think we should give it maybe a few minutes. It's, I guess, right top of the hour right now. What do you think?
Sure. I also have no idea how well this has been advertised.
Yeah. Yeah, it's always a little difficult to just speak to a recording, but I guess we will do the best we can.
Yes.
What do you think? Wait until 5 after the hour?
Sounds good to me.
Okay. Okay, I think we should get started. We've been alerted that many of the participants will be watching the recording. So for those of you who are watching the recording, it won't be quite as interactive, but for those of you who are here, please feel free to raise your hand and we'll try to address your questions as they come up. I am Edward Lee. I'm a professor at Berkeley. I've been a professor at Berkeley for, well, I've been at Berkeley for more than 40 years. I started there as a PhD student and then never left. And I've been working in the area of embedded software ever since I started, although that field didn't really exist by that name in academia at the time. I'd like to introduce Martin Lostra, who is partnering with me on this presentation. Martin is a staff researcher at Berkeley who completed his PhD under my supervision at Berkeley and then became a postdoc at Berkeley and then became a staff researcher. So he has also been at Berkeley for a while. And we are both co-leading the Lingua Franca project, which is a fairly substantial international effort with many major participants, most of them in the US and in Germany, but a few others in various other places in Denmark, for example, and a few others. So we'd like to start with giving you some of the motivation for the project, and I'll turn it over to Martin to do that.
Excellent. Thank you, Edward, for the kind introduction. And it's a pleasure to do this tutorial together with you today. So let me start by sharing my screen and indeed go through some background and motivation. And then after that, we can roll up our sleeves and do some programming. So the problem that we're addressing, let me go into slideshow mode. So the problem that we're addressing is that even though there's been major advances in programming languages and compiler design over the past many decades, there are still two major problems that pose a lot of practical challenges to programmers today. One of them is concurrency, and this image here on the left you might recognize as representing the dining philosopher's problem. If you have to deal with concurrency at a low level, you're exposed to all sorts of challenging problems related to locking, deadlock, and these problems can be somewhat avoided by using frameworks message passing frameworks, for instance, where there's less shared state, and instead of having access to shared variables that you have to protect with locks, you exchange messages. But there too, you expose yourself to non-determinism, which makes it incredibly difficult to get the behavior out of the concurrent programs that you write that you actually want. Another problem is that it's incredibly challenging to specify timed behavior in most common programming languages. So usually if you're interested in doing something timing related, you're stuck, operating in some while loop and then maybe referring to a timer or hardware peripheral if you're doing it at a low level, or if you're doing this on an operating system, you have some jiffy interval that you can tie yourself to. But it's all very imprecise and platform dependent, and there's very little tooling to actually assure that any kind of timing requirements that you might have can actually be satisfied in the program. Now, this is in part also because most of the programming languages that we use today are geared towards computational systems. And computational systems are markedly different from cyber-physical systems, as the audience of this talk is probably well aware of. Of course, with computation, you're interested in turning some input into some output, and when the program terminates, you declare success. And if you do this faster, then you might have written a better program, but this program is better only in the sense that it is more performant. It's a performance criterion. Whereas if you're doing something cyber-physical, so you have software that interacts with an environment, then if the timing is off, not even necessarily faster or slower, but just not up to spec, like this juggling act that is represented here on the right, then of course the program fails. And like the program on the left, where you're interested in the program terminating, termination of the program in the cyber-physical context is usually an outright failure, right? So these kinds of systems are very different, and they ask for different programming models. So the non-determinism that I mentioned, and that is also featured prominently in the title of this tutorial, just to illustrate that this is actually a very practical problem and not just some academic problem. We studied AutoSAR AP, which is a relatively new extension of the AutoSAR standard. AutoSAR is a software stack for automotive applications that is heavily used in Europe predominantly. And with the advances in hardware and the desire to build more dynamic systems that maybe have machine learning components in them, and video feeds and all sorts of more computationally heavy services, there's been a move from
Hello.
Martin, we seem to have lost you.
Okay, it's not the only one. I mean, I'm not the only one who cannot hear Martin.
Oops.
Oh.
What happened?
He's kicked out. Oh, he's back.
He's back, but muted.
my connection just got killed. I have no idea why, but I'm back. Okay, let me get this out of the way. Oop, that's the opposite of what I wanted to do. Okay. So with these more dynamic frameworks, it is possible to compose activities perhaps more dynamically, And the frameworks are set up in a way often to present to the programmer an interface that is very sequential, but behind the scenes, what's happening is that there's an exchange of messages. And so if you look at this code here, which any programmer would say, oh, well, you're setting a value, then you're adding 2 to it, they wouldn't guess twice what the outcome of this program should be. But if you actually run this program, because there are asynchronous message exchanges happening under the hood, the actual outcome is highly non-deterministic and not at all what a programmer might expect. In actual applications, this poses practical problems as well. Aside from this little demo code that I showed. So we considered this demo application put out by AutoSAR, where they show a pipeline that starts with a camera that delivers images, and there's some adaptation of the image and pre-processing. This then gets piped into a computer vision component that has to recognize cars in the image, and then eventually do brake assist. Now, this is a pretty straightforward, not very complicated architecture. This is really just as a pipeline, right? But because underneath there's asynchronous message exchange, and there's no actual control of the order in which these things happen, there can be dropped frames. Well, that might not sound too serious, but it can also lead to mismatched inputs. So the component, like the computer vision component, will get some information from one sensor, and it will get a video frame, and these things are mismatched. And so this can actually lead also to dropped vehicles. So there's actually vehicles in the image that don't get recognized until a later video frame. And so this can be pretty dangerous, and it makes the software hard to verify. This is not unique to AutoSAR. We also looked at AutoWare, another automotive software stack, where we specifically looked at a valet parking demo that was put out by AutoWare, where a car is navigating a parking lot, finds a parking space, and parks the car. And so there are lots of components in this software architecture, which is based on a publish-subscribe mechanism delivered by Ross, and highlighting just a small portion of this architecture. We can see that because there is a reporting of the vehicle's kinematic state, and also a report coming in from another asynchronously reporting component that reports the state of the gearbox, the program can end up in a state where the velocity indicates that it is going forward, and the gear might be in reverse or the other way around. Now, this, of course, sounds very troubling if this were to actually occur in reality, right? And the fact that this can occur just as a consequence of the underlying software infrastructure robs the designer of the ability to actually recognize this as a failure. It's just a fact of life. So what you'll do is have to ignore it when it happens, which means that you can't really act on it when it actually happens, right? When there's actually a crash, and the car is being pushed in the opposite direction by an obstacle that it crashed into, or another car, right? And as troubling as this sounds, the discovery of these kinds of really tricky corner cases is incredibly difficult. This is illustrated by how often we had to run this software in order to pick up on these problems. So you can see here, if I remove my Zoom window, this is out of 300,000 tests that were run. We get a number in the sub 1% range of out of order message sequences that lead to these kinds of inconsistent views of the state of the vehicle. And so, of course, if you just run a test, and you might run one every day, you can do this for a year long and not run into this problem. But of course, by the time that the software gets deployed in real cars, and these cars will all drive for many, many miles, then eventually this will happen. But it's incredibly difficult to prove the absence of such problematic behaviors using a model that can deliver these behaviors completely unexpectedly. So obviously, there's a great opportunity in front of us in terms of, like I said, there are major advances in hardware. The hardware is faster, it is more power efficient. There's lots of great things that can be done with that computation power, but it comes with challenges as well, because in order to do that reliably and safely, we need some kind of principled approach and effective tools to ensure that indeed is the case. And this challenge is not just limited to the automotive field, but it also is there in critical infrastructure. So think of power distribution networks, industrial automation, robotics, but also in cloud systems, right? And this moment of opportunity and challenge, must have also occurred in the 70s when people started building the first microprocessors and realized, well, this is incredible. If only we could put more transistors on a chip, then we could do great things. And this is where we are today, where we don't have thousands of chips, but we have thousands of transistors, but billions on a single chip. There's absolutely no way that designers could build those by hand. The challenges that they were facing were also concurrency problems and timing problems, right? To make these chip layouts that would work with a very high cost of failure as well. If you don't build your chip correctly and then send it off to be made, the cost will be tremendous if there are mistakes in it. So without the tools that hardware designers have today, they wouldn't be able to deliver this hardware that we now get to benefit from. So I guess our view is a little bit along the lines of, well, if the challenge was, if we've managed to address that challenge, then what is our excuse as software folks, right? Perhaps we should build software more like we build hardware. And so the lingua franca approach here, going back to those two challenges that I sketched, concurrency and timing, essentially takes those challenges away from the programmer and lets the programmer focus on the business logic of the application. The programmer will only have to write simple reactive code, and the coordination of these reactive pieces of code is dealt with by a supporting runtime system that automatically deals with the concurrency, exploiting parallelism, and making sure that things are scheduled on time. And then the programmer can focus on componentizing the software and composing it using this coordination language that we offer. Once compiled, the code is executed with the help of an advanced runtime, and we currently have runtimes and target language support for several target languages. What we will focus on today is our C implementation, but we also have a C++ implementation, and we have a Python implementation that actually builds on top of the C runtime. We also have support for Rust, and we have support for TypeScript, and we have IDEs that you can use to build lingua franca programs. And one really nice aspect of this mechanism is that because the the components are specified in lingua franca in such a way that the structure of the program is accessible to the tooling very easily. We dynamically create diagrams out of the software as you type your programs. So if you have, an ordinary imperative program, of course you can do control flow analysis on it, and you can essentially build diagrams out of that. But our composition mechanism has a data flow flavor to it that makes it very obvious what the structure is, and that really helps people view what they're doing in terms of an architecture and component architecture that they're building. We will go into more detail when we look at the code. So one thing to say about this approach is that we can actually leverage the same paradigm at different scales. So we have support for bare iron currently we support the RP2040 chip. We also have support for the NRF 52 bare iron, but we also support real-time operating systems. Currently we have support for Zephyr, and we are also working on FreeRTOS. So those tiny chips we can target, but we can also target POSIX systems. So there we have the advantage of leveraging thread libraries as we do on RTOS, but then POSIX threads. And it is also possible to make a lingua franca program federated, which means essentially instead of taking the program and exploiting concurrency at the level of threads, we can take the lingua franca program and farm it out into separate processes that jointly deliver the same behavior that you would otherwise get from the program as it runs in a single process. So we can also target clusters and bigger compute systems like that. So now the question, of course, well, you talk about determinism. Lingua franca is by default deterministic. Now, what is the cost of this? Because we've all seen the great success of asynchronous message passing and the tremendous performance that it can deliver. So how does lingua franca stack up against actor frameworks, for instance, that are commonly used in industry? Well, we did the analysis. We implemented a benchmark called Sabina, which is an actor benchmarks. And so, of course, the underlying model of lingua franca is related to actors, but it's not quite the same. So the components are not called actors, but reactors, and their communication is more restricted because we enforce a strict order on the handling of certain events. But it turns out that when we compare head-to-head the implementation of these benchmarks between lingua franca and Akka and CUF, we actually do better. We're faster. So it's not that we have to pay a price to get determinism. In fact, we can actually compete, and in many programs we are faster. To explain why we are faster, if you have a message passing system where there's no ordering of message arrival intrinsic to the model of computation, you often have to do a bunch of extra work to actually achieve the programming behavior that you want. So there's some coordination that has to happen in the application code, which might involve creating state machines in the components to track the state of other pieces of the system, or to do some locking or mutual exclusion control. And because those things are taken care of by the semantics of lingua franca and the runtime system that supports it, we can do that much more efficiently. And so what we have observed is that the programs tend to become simpler and faster. Now, this determinism stems from our model of computation that is very synchronous. So reactions to events occur in a very synchronous manner, and you can also make the programs more asynchronous. And what this really amounts to is trading off consistency, which you get perfect consistency if you respond to events synchronously, but if you were to loosen this and introduce additional delays, you can increase the availability in the system. Now, I won't go very deep into this because Edward will talk about this later during his part of the presentation. But my main point here is that it's not an all or nothing proposition. You don't have to go all asynchronous like with actors or all synchronous. There are ways of navigating this trade-off. So in Lingua Franca, the communication between components happens through tagged events. When I say tag, you should think of a timestamp. There's a technicality to this is that we also carry a microstep for those familiar with the concept of superdense time, but that's not really important for this tutorial. And what these tags are used for is to establish a logical ordering of events. So an event can just be thought of as a value. So there's a combination of events, which are values, with tags, which are you can think of them as timestamps or numerical values that order those events. So this is what gives the semantics to the message exchange. The tags are also used to establish a relationship with physical time. So the physical time at which events get handled, we want to also align or bring as close as possible in alignment with physical time. If you are interested in real-time behavior, then we have to impose bounds on the deviation between these two. So one thing to keep in mind is that in Lingua Franca, there are actually two timelines at play. There's the physical timeline, and then there's the logical timeline. And the logical time at any point can be thought of as a tag of the event that is currently being handled. And the physical time is really just something of numerical value that you read from a clock, to get the wall clock time. And now it turns out, again, referring back to this trade-off between consistency and availability, which for people who work in distributed systems is a well-known concept. This CAP theorem postulated by Eric Brewer that I mentioned here on the previous slide, that if the network gets partitioned, that you have to give up either consistency or availability. What we say is, well, partitioning is really just an extreme case of delay. If a network gets cut in half, then it just has a very long delay between the two parts, and so we can replace the the P with an L and reason about the delays in the system quantitatively. And so by manipulating the tags of the events that we have, we can perform this trade-off. So what's interesting about this is that in Lingua Franca, we have some explicit way of navigating this trade-off, whereas if you're building a distributed system, you can talk about this trade-off, but it's very hard to actually make the trade-off in your code and quantify it and reason about it. So what I will be focused on during the remainder of my talk, so I have about half an hour left before I hand over to Edward, is I'll quickly show how to install Lingua Franca on your own machine. And then I'll go over some very basic programs to explain the language concepts, and also talk a little bit about causality and causality loops that you might encounter when you write Lingua Franca programs. Then after handing off, Professor Lee will talk about the running LF on embedded systems, specifically the RP2040 that we can target as bare iron using our C target. And these examples will also go into an extension of the language that was recently made by Alexander Schultz-Rosengarten called modal models. That are very effective at organizing lingua franca programs that have modal behavior. Then there's also some time to talk about federated programs, and again, I'll go a little bit into more details about this trade-off between consistency and availability. So let me switch to my console instead. I hope that this is visible. I'll make it a little bigger. So I created this directory ES week, which is empty. To install Lingua Franca, you can go to the download page, and there is a little script that you can run to install the command line tools, as well as our IDE called Epoch, as well as there's a VS Code extension that we'll be using, and that can just be retrieved from the marketplace. But if you run this command, which just downloads the script and runs it, you will see that it will download this command line interface tools package. And if you have the installation directory on your path, then you can type which LFC and find it. LFC is our Lingua Franca compiler, and if you type LFC version, you will see that this is version 051, which was released earlier this week. If you're interested in using the nightly build of our CLI tools, then you can just type nightly, and then you'll get the nightly version installed instead. Okay, so we are in this ES week directory, and I'm just going to create a directory called SRC where I'm going to be putting my sources in, but I'm going to designate this directory here as my project directory. So I will fire up code in this directory. As mentioned, we have an extension published on the marketplace. So if you look that up, you can find us here. You can download and install it just with a single click. And as with the downloads and installation script, you can switch to a pre-release version, which I currently won't do. But that gives you access to the nightly built version of the extension. So we can start out by creating a new Lingua Franca file. As I mentioned, Lingua Franca is polyglot. We have support for several different target languages. The first thing that you have to do when you write your Lingua Franca program is specify which target you're going to be using. Like I said, for us, that will be C. So I will specify that we're going to use the C target. So let's first try to build a little hello world program. So let me save this. That's allowing me. Let's call this demo.lf. So we now have our file demo.lf, and we can already see the squiggly lines here. The compiler wants us to provide some more information. This is not quite enough for a valid program. So let me first create a new component, and let's say that we want to build a little control pipeline. This is common in cyber-physical systems where we want to have some sensor, we want to implement some control, and then we want to have an actuator to actuate something in the physical world. We won't do that in the sense that we won't program any hardware during this part of the hour, not any embedded hardware. but we'll just use my console to print something. So let's say we have a sensor here. So this defines a reactor class, and like C programs or Java programs, in order to give a starting point for execution, we have to specify a main reactor. And that allows us to now save the program. And this is still not a valid program because it doesn't really have anything to do. It says there are no reactions, right? Okay, so let's zoom in on the sensor a little bit. And we're first going to just do a hello world here. So I create a new reaction, which we say is triggered by a built-in trigger called startup. And then I specify as the code that should be invoked when startup happens, just straightforward C code, which is printf statement here. Hello world. And these delimiters here tell the compiler that now we stopped writing Lingua Franca code and we started writing C code, right? Lingua Franca doesn't require semicolons, C does, so be sure not to forget those. And now I can create a new instance of this sensor. Let's call it S. And now we can try to compile this, run it. And indeed, we printed hello world here. There are some additional output that show statistics in terms of the timing, but we can ignore that for now. So now let's say that, well, this was only printing hello world once, so how do we go from here? So let's say that our sensor is a periodic sensor. It pulls some piece of hardware with a regular interval. So being triggered at startup is not quite enough. We can add a logical action. Let's call it A. And we can add it both as a trigger as well as an effect, which would allow us to schedule the next event. So we can do LF schedule A and say, well, schedule this same reaction to occur a second later. All right, and now we should have some periodic behavior. Let's see if this works. This works. So now every second we get hello world. And we also provide some convenient syntactic sugar for this called the timer. So let's simplify our lives and not do any manual scheduling, but just use a timer. So with the timer, we can just specify as part of the timer what we want it to do. So we specify an offset, which we say is 0, and an interval, which is 1 second, and this should give us the same behavior. So now we have a simple sensor, and now we might want to hook that up to an actuator, right? Oh, this should be reactor. And to do that, of course, the sensor needs to have an output port. So let's say that we just want to report some numerical value, so an integer. And instead of printing hello world, in fact, let me move this reaction hello world here to the actuator. And give this actuator an input, also of type int. and let it be triggered, let the reaction be triggered by that input. And now instead of printing hello world, I'm not going to print hello world, but I'm going to print the numerical value that I get from the input. So I can say imp value is the thing that I want to print here. Okay. Now I have an actuator with an input and I have a sensor with an output. And what I will want to do here now is to use the API LF set to set the output to the value that I'm interested in. Let's make it 42. And now I'm going to save it and I'm going to compile it. So the key combination that I'm using here is Control-Shift-P. This opens the command palette, and then I can choose Lingua Franca build here. And then I already know that it's going to tell me that there's a problem here, because what I'm doing is I'm trying to set an output that I didn't declare as an effect of this reaction. Now, the reason why the compiler needs to know this is because you can think of the Lingua Franca program as a dependency graph that you're specifying. So the thing that I forgot to show here is that as I typed all of this, graphics are rendered that represent the graph. So we have our sensor here with a timer, and we have our reaction here, and I click on the diagram and it highlights the reaction that this relates to. And what we forgot to do, okay, so this kind of visualizes the structure of the program, but what the runtime has to do is schedule the reactions in the program to occur such that data dependencies between the reactions are preserved. And to do this, it needs to know, at least abstractly, what these reactions do. Okay, so if I don't specify out here as a potential effect, that's it won't allow this reaction to access the output port. But if I specify it as an effect, then now I can write to it. But as you can see, we're not doing anything with this output, so that won't be very useful. So let's also create an actuator. And build a connection between the output port of the sensor and hook it up to the input port of the actuator. And you can see the diagram updates. So we can see here the sensor with the timer, and we can see here the actuator. So now we've established a data dependency between this reaction and that reaction. That is because the reaction here is triggered by this input. This input is hooked up to the output of the other guy, and the other guy has a reaction here that outputs it. So now the runtime system knows to execute this reaction before that one. Okay, now let's see if this works. Yes, this works. And of course, we can now also hook up something in between to do our control. So I'm just going to add a controller. We're not going to do anything fancy because we don't have time for that, but I'm going to create an input. And I'm going to create an output. I'll create a reaction going from imp to out. Oh. And I'm going to say, well, let's set the output to the input value times 2. So I'm just going to multiply it here. And then if I hook up the sensor to a new controller, and put the controller before the actuator then we should see that when we run this, instead of printing, oh, there must be an error somewhere. What did I do? Ah,
You're
I
missing
forgot.
the semicolon.
Yes. So now it's printing 84. So now there's some technicality that I would like to show. I'm going to keep this really simple, but if you add a reaction here in the sensor, or actually, let's do it in the controller, it doesn't matter. I'm going to add a reaction. Also triggered by the same input and writing to the same output. And I'm just going to set it to 1. What we will see is that this program is valid. There's no problem here, but it consistently outputs 1. The reason for this is that the order of declaration of the reactions within a reactor also impose an ordering constraint. So if these two reactions are triggered at the same tag, then first this reaction executes, and then that reaction executes, and the latter reaction simply overrides the output. But this doesn't matter because the output is not observed by the actuator before both of these have concluded. So the only output that ever gets observed by the actuator is the last value, which is 1, right? So this is related to the concept of sequential consistency. No, sorry, I'm blanking on the term, but this is a mechanism that is also used in SC charts. I think it's sequential constructiveness. And what we can do now additionally is, because we have this pipeline here, is we might have some additional constraint on the timing of this, right? So we might want to say, well, we want to actuate, but we want to make sure that we actuate quickly enough to respond to the input that is gotten from the environment. So we can add a deadline here and specify, let's say that this deadline here is 10 milliseconds. That should be easy to meet. And if it doesn't meet that deadline, I'm just going to print oops instead of the actual print that we have here in the ordinary reaction. So what this means is that, and let me walk through what actually happens based here on the diagram. So this timer causes events to be enter the event queue with a certain tag. The runtime system handles the event soon as the tag matches the current physical time. That's when the event gets released. Okay, that's when this starts executing. That produces an output that then triggers this reaction to occur. The tag is still the same, so this is a logically instantaneous reaction, and then it arrives here, and the tag is still the same. So the tag that it had here is still the same tag that we have here, but of course physical time will have moved along because it takes physical time to execute these reactions. Now, what the deadline says here, put a bound on the discrepancy between the logical time and physical time. And of course, if I run this now, I won't reliably trigger this deadline handler because 10 milliseconds is a lot of time. But I can tighten this. Oh, forgot a semicolon again. But I can tighten this and well, I don't know. Let's try 1,000 microseconds. See what happens. Of course, my machine now is using Zoom, and there's all sorts of interference. So it's not really clear whether it will be able to deal with this. Well, it looks like it can. Let's see if I can bring this down or make it even 50. That for sure should trigger the deadline to occur. Now, the utility of this deadline is twofold. First of all, it gives us a fault handling mechanism. And second, once we built more smarts into the compiler, our eventual goal is for the compiler to tell us, based on analysis of the structure of the program, which here is clear because we built the composition in Lingua Franca, and we have all these dependencies that are available to us. Combined with the worst case execution time of these reactions, that the compiler would tell us the deadline that you're given actually is feasible or not. We don't have this capability in our compiler yet, but we plan on building this. So this gives us a very nice way of specifying timed behavior, and it gives us a way to deal with deadlines. Now, if you so far we've only talked about things that are very nicely aligned in logical time, but what about spurious events or sporadic events? So what if somebody presses a button at some random time, or a sensor gets tripped by some event in the physical environment? What tag do we assign to an event like that? For that, we have physical actions. Now let me change directory to our Lingua Franca playground. Playground, and go to our examples. And compile a program called Reflex Game. Which is a very simple program that prompts the user to press enter, and it does this at some randomized time, and then whenever the user enters, it records the physical time as it is available from the operating system. And then it computes the time difference between the time at which the prompt was sent out and the answer was given. So you can see here, this records my response time. So let's have a quick look at the program. Computer is being a little slow. So let's visualize this program as well in the diagram editor. So there's a get user input reactor here, which so this is the startup action that triggers this reaction that sets up a a thread that is able to asynchronously monitor the keyboard, and whenever that that happens, it is able to schedule an event in our system, but it uses the physical action for that. And what that means is that it doesn't schedule it relative to what the current logical time is, because there is no well-defined current logical time, but instead it uses the current physical time. And because our runtime won't start handling events before logical time meets physical time, it is safe to insert that into the queue, and it will get handled soon as it's simply the first event in the queue. So I can zoom in a little bit on the code that invokes schedule. So here we just have a simple while loop in this external thread that we schedule, and again, we're not doing any locking or anything like that. We just say, okay, here is the schedule function. This is a schedule API. Under the hood, of course, we have to do some concurrency control, but the user doesn't have to do it. And this safely inserts this event into the event queue. Now, there's one subtle thing that I would like to discuss before I hand over to Edward, which is this notion of causality that is inherently captured in our model of computation. That is, I think, a very nice feature, but also treacherous, because sometimes it can lead to problems called causality loops. So you're all familiar probably with the game rock paper scissors, which is just a simple game to break ties. Right, so there are two people who shake their hands in synchrony, and then instantaneously at the third shake, choose rock, paper, or scissors. The rock defeats the scissors, the paper defeats the rock, and the scissors obviously defeat the paper. Now, of course, if you want to cheat this game, you can by slightly waiting for your opponent and let them choose, and then quickly choose the response that would defeat it. So this game here, it's not an interactive game. It just uses a random generator, a pseudo-random generator to play this game. But it has a class, reactor class here called player. It takes a parameter which allows you to spawn different players and distinguish them. And then in this program, these players play against each other. And I can run it really quick. So player 2 chose rock, the other one chose paper, the other one chose rock, and player 2 won. So I can show you the logic here of the player, which is at startup, it figures out a random seed here. Then it reveals first its choice, and then it observes the choice of the other player. And if it's the same, then it repeats, and otherwise it declares victory, right? Now, because this is a single class and we have two instances of it, obviously, think about the game. You can't have two players that both cheat. If Edward and I were to play this game and I wait for Edward and Edward waits for me, then nothing would happen. We would enter a deadlock. And if we were to implement this program in say, an actor language, then we could have these actors and they could try to cheat on each other, but there would be no way to figure out that there is actually a problem we would run the program and we would see nothing happen, right? That we would just have a deadlock occur. Now, because there's this strict notion of causality that's being preserved in the semantics of the language, we actually can detect this at compile time. I can simply make this into a cheating reactor and switch these two guys, meaning that now first I observe the choice of the other player and then reveal my own choice. Then our compiler says, well, you can't do that because this is not causal behavior. I can't schedule this. There's no way to schedule this. And therefore you need to resolve this this causality loop. So even though the reflex game here, for instance, has a cyclic structure, because there is a cyclic connection between the user input and the random source, if you look carefully, the reactions actually form a tree. They're not a cycle. Any valid lingua franca program cannot form a cycle. And if you get this kind of error where it says you have a causality loop, then that usually indicates not just an annoying problem, like type checker would tell you, well, this program won't work. Usually what the type checker tells you is like, hey, you did something that is actually a programming error. This is not what you meant. And so this is actually a pretty subtle concept, but soon as you learn to deal with it, you'll find out that the compiler actually gives you a lot of help. So I just wanted to bring that to the attention of lingua franca users, and then hand over to Edward to continue the presentation from here.
Thank you, Martin. That was great.
Martin, can I ask a couple of questions?
Yeah,
Yes.
for sure.
Oh, okay. First of all, thank you for the great demo. It was really helpful to understand the concept of the lingua franca. Thank you so much for the helpful demo. So I have a couple of minor questions. So the first one is, can you have multiple targets in a single file?
Great question. I had the same question a couple days ago when I did this talk at ASU, and the answer is not yet, but we are very close to being able to do that. So specifically in a federated program where each of the top level reactors become their own process, really the only thing that needs to be done is to ensure that they use the same serialization format for the messages, but then that would be practical. So this is something that we have on our agenda for creating. It's not possible yet, but it will be possible in the near future.
Great,
I'll be
good to know.
showing the federated execution, so you'll get a sense of how that would work.
Would be great. Yeah, the other question that I have is kind of minor questions. So usually when it comes to modeling language or coordination language, we tend to, take graphical approach, just like your Ptolemy tool, right? I mean, we kind of prefer having, this graphical representation like this. We can enjoy all this, reusability. We can just drag and drop all these components. But, in this lingua franca case, you did exactly the other way around, right? So is there
Yes.
any particular reason for that?
Yes, there is. So obviously there's a lot of value in the diagrams themselves. It's a great way to communicate and to kind of introspect programs, to talk to people's across layers and development teams. Some person might be a low-level programmer, another person might be an architect, and it's a great way for them to agree on what the architectural layout of the program should be. So there's a lot of value in this, but at the same time, it's also kind of onerous to as kind of a programming model to drag boxes and connect wires, especially when the programs get bigger. And we realized that for bigger and more complex systems, just having a programming language approach with a normal textual syntax was actually better. And one of the key reasons, and we actually learned this from our colleagues at Kiel, is that there are many useful views of the program that can be synthesized at will. And if you don't, if you put the control of what the actual diagram looks like in the hands of the programmer, they will just construct one view that's useful to them. But there are actually many views that are useful. You probably saw that there were some things that I expanded and collapsed. And that's one aspect of that. But in general, to have the layout problem be solved by an automated system and then have choices in how you actually visualize the program turns out to be really valuable. So that's, I think, probably the biggest strength of this approach when compared to just a diagrammatic programming approach.
Yeah.
Yeah, to give credit where credit is due, we really have to credit Reinhard van Henksladen's group at Kiel University, because they have really mastered this problem of automated layout, and that's a key enabler. Initially in Ptolemy 2, we didn't have that, and you know, building programs could get pretty tedious, where a lot of your editing was managing the layout. They built an automated layout tool for Ptolemy 2, and that's part of what led us down this path, because we started to realize that this could be very effectively automated.
Right. I mean, I was also working on this, formal model and that kind of thing. Even if I encourage you to use this kind of tool, that the biggest barrier is kind of this one. I mean, they hate, figuring out how to, follow this, semantic. And what I found out extremely useful from your demo is that, you give this visual feedback. I mean, this about, tree versus cycle thing, you give this visual feedback to the designer that you are making now cycle. I found it is extremely useful for the designer. But you do allow this, Lingua Franca programmer to use this tool in a purely textual mode. I mean, even if they don't have this access to this IDE or Eclipse-like thing, they can use it, and they can still have this textual, feedback, right?
Yeah, that's right. The command line tools have no dependence on the graphics engine.
Mm-hmm. Great,
yeah.
Thank you.
And one other aspect here that is really important is that because we have this textual approach and we have this mixing of lingua franca syntax and target language, we can effectively blur the line between what is the deployed application and what happens at the very beginning of the design cycle, right? Because oftentimes there are modeling languages that are being used, and they look more like Ptolemy or Simulink, right? And then at some point there is a break with that, and there's going to be either some code generation or there's going to be a complete new implementation effort that takes that initial design and then translates it to the thing that will ultimately run on the microcontroller or whatever it is that the target is. But for us, there's really no material difference between the design artifact and the deployed artifact. They're the same.
So I'd like to actually illustrate that point with this next segment. So what I'm going to do is actually show you a very nice extension to the lingua franca language that was constructed by Alexander Schultz Rosengarten, who is a PhD student of Reinhard van Henksladen at Kiel. And we use this extension pretty extensively in our instructional courses. And I'm going to show you writing a lingua franca program for this robot, which I'll tell you a little bit more about as we go. But let me share my screen.
Sure.
And I'm going to start with is essentially a minor variant of the same program that that Martin was showing you, which is a sense, process, actuate chain. And in this particular example program, there's not much of interest going on as the ones he showed. It's just the process is, the sense is generating a counting sequence. The process is multiplying that by 2. And the actuate is just printing the value, okay? And we can just compile and run it. We can see the result of the compilation here. And I'd like to emphasize what happens when you compile this, right? So in particular, in this directory where there's this source file. So in this source file, I have this sense process actuate file, and that's the one that I compiled. When I compiled it, it created a binary that is in this bin file, but it also created a source gen directory that has a standalone C program. So it's an important thing to understand about Lingua Franca, that when the Lingua Franca compiler runs, it generates a program in the target language that is now, it's got the generated directories here have all of the infrastructure that's required to run this program. So when I run this binary, all it's going to do is produce this doubled counting sequence. Okay, so not so exciting, but let's make the program a little bit more interesting. Let me as a backup, I'm going to just copy this file, create a new version of the file in case I mess up and have to back up. But let's give the processing a modal behavior. Okay, so in particular, what I'm going to do is I'm going to define a pair of modes. So an initial mode, whoops, I misspelled initial. An initial mode A, okay, and then I will have a second mode B. Okay, that won't be the initial mode. And I'm going to give a slightly different behavior to each of these. So in particular, let's keep the original behavior in the initial mode. Okay, and in mode B, let's instead just negate the input value and not multiply by 2. All right, so now the idea is that there's 2 different modes of operation of this processor, and I haven't switched between them, so the behavior will be the same as before because I'm just going to stay in mode A. But let's create a switching between modes, and the way that I do that is I specify that mode B is a possible effect of this reaction. And maybe I can write arbitrary C code here, but let's say, whoops, it has to be correct C code. Let's switch when the input value has hit a multiple of 4. Okay. At that point, I will set the mode, whoops, to B. And now there's going to be a transition after 4 executions of this reaction. And we could do something similar to switch back to the other mode in this second reaction on the next multiple of 4. So let's switch back to A.
You have a typo after LF set. There's a plus there that doesn't belong.
On which line? Oh, yes.
In both, right?
Yeah,
In
got it.
25, yeah.
Okay. Yeah. So now we have a state machine. Okay. And, again, this is a pretty small program, but these programs can get fairly large. I'll show you an example in a minute that's not quite so trivial, but there's this nice hierarchical browsing availability. So you can now see that it's got 2 modes of behavior. You can examine the modes individually or in combination, and you can ultimately show all the details of the program. Okay. And so now if we compile this version here and verify that, yeah, we got a correct compilation, go back to my terminal and run the binary again, we should see the first 4. Whoops, what did I do wrong here? I know what I did wrong. The C code that I wrote here is always going to return true. I meant to do a comparison against the value 0, right? So this is if the input value modulo 4 is equal to 0, then I'll switch to mode B. Similarly here, if the input value is modulo 4 is 0, I switch back. So we'll try that again. Go back to my terminal. Whoops, what did I do wrong? I did something wrong again. Help me out here, Martin.
Yeah, I'm also looking, but I'm not seeing it.
Maybe I didn't actually recompile this. Did.
So it never switches to mode B, right?
That's what it looks like, but I don't understand why that is. I did, in fact, try this before. So I'm not, it's one of those phenomena where we're just not seeing it.
Do you have a copy of that earlier thing that you tried?
Yeah, I do.
You can just run a diff.
Well, wait a second, though. I just put in an additional printf in here, and that's not showing up.
Oh, whoops. Compiler didn't finish.
Do you want to try to compile it with LFC?
Let me make sure that I'm actually in the right place. Oops. Yeah. This is really weird. Oh, of course, I'm running the wrong binary.
Oh, how did you have to
Oh,
run the second one, right?
It's always something simple.
Right.
I was simply running the wrong
Oh,
binary.
we got it.
Yeah.
We got
So
it.
now it's working. Okay. Let's get rid of that debug statement. All right. So now we've got these two modes of operation with two different behaviors. So this notion of modal models is actually extremely useful for building up more complicated programs. Now, of course, you could just do this in C code in the body of the reactions, but there's enormous value in having both the structured representation in the textual code, but then also getting the graphical rendition. So what I'd like to do next is show you an example of a use of this that running on this particular robot. So this is a very rather elegant little, rather inexpensive little robot from Polulu that we were using in our instructional classes, and it has a RP 2040 microprocessor on it, which is the one that's used on the Raspberry Pi Pico, which is, here is an instance of the Raspberry Pi Pico. It's a pretty popular embedded platform. has exactly the same microcontroller. It's a dual core ARM processor, and we run it bare metal. So there's no Linux system running on it at all. And I'd like to show you one of the programs that we have students build in the course that we're teaching in embedded systems. And one of the goals that they have is to get the robot to drive in a square pattern. And this is using a variety of different sensors. So it uses the encoders that are attached to the motors on the robot. The students construct code to convert the encoder data into measures of distance. And then there is a modal behavior here, which switches between driving and turning. So the idea is that the robot will drive for a certain distance and then switch to turning mode, where it then uses a different set of sensors to rotate its behavior. Okay, so I'd like to show you from, first I'll just run this program. So what do you need? Well, you need this Pololu robot, and you need a USB cable, and you plug in the USB cable and you plug that into your laptop. I'm using a Mac in this case. And then you hold down a pair of buttons on the Pololu robot, which puts it into a boot select mode, they call it. And when it's in the boot select mode, it actually appears on your machine as a disk drive, and there's a tool in which you can download the program. So let me first compile this program. Okay, so the first thing I'd like to show you is that what gets generated is a little bit different now in this case. Let's get zoom out of the way. If I go to the terminal and look at the bin directory now, a binary file called robotsquare.elf was created. Now, why was that created instead of the C program? Well, if you look at the target specification at the top of this program, one of the things that we support is being able to define platforms and even specialized boards within a platform. So in this case, the platform is an RP2040. The target is still C. The platform is an RP2040, which specifies the microcontroller that we're going to use. The Pololu 3Pi 2040 robot is the particular robot which has particular connections, additional hardware beyond what the RP2040 includes, and particular connections to that hardware. And this tells the code generator which header files to use when it goes and compiles its code. So I can download that code onto the robot using this Pico tool, which is widely used among Raspberry Pi programmers. And that will flash it onto the robot, and then and actually start executing it on the robot. So now I've got the robot here, and when I power up the robot, it'll start executing this program. Right now it's powered off because I unplugged it from the USB. But let me stop sharing so that you can get a slightly more complete view of things. And what I'm going to do is aim my laptop at the floor here and see if I can get this robot into view on the floor right there, and I power it up, and it's programmed to go a certain distance and then turn, and then go an equivalent distance and turn again, and it just keeps repeating that. Okay, so again, not very exciting, but I'd like to show you how the program works. And it will give me an opportunity also to show you a few of the rather nice features in Lingua Franca. So go back to screen sharing, go back to this picture. Okay, so let me focus on the turning mode. All right, so the turning mode, I can zoom in on this. When I'm in the turning mode, I'm getting a measure of the amount of distance that the robot has traveled. Okay, but this is really just, if I look at the, let me zoom out again. The program is being triggered ultimately at 10 hertz here. So there's a timer that is triggering every 100 milliseconds. That's causing an encoder reading, which is then providing encoder readings to these angle to distance components, and then that is providing a 10 hertz input to the robot state machine. And then there is this gyroscope component, which is taking a reading of the gyroscope on the robot, and then integrating the result using a trapezoidal integrator, and then using that in this reaction here to check the gyroscope angle reading against 90 degrees, and then to switch back to the mode of driving when the gyroscope has rotated by 90 degrees. Okay, there's a couple of subtle points that I'd like to show you about how this is built. But to do that, let me first go and find the implementation of the gyroscope code. Okay, so I can just follow the code in the IDE. By the way, the IDE that I'm using here is not the same as the one Martin was using. Martin was using Visual Studio Code. This is an Eclipse-based IDE that we call Epoch. They both have pretty much equivalent functionality, but it's nice to have alternatives, I think. So, so this gyro angle component includes an instance of this gyro component. And here I can show you that this gyro component makes use of a inheritance mechanism in Lingua Franca. So in particular, this is a really small reactor definition. Okay, it because it extends a base class, which includes some basic functionality. So in particular, on this robot, there's an inertial navigation unit, an inertial measurement unit that includes a gyroscope and an accelerometer. And both of these get initialized together, okay? And you might have multiple instances of these reactors in your program, and you want this initialization to occur only once. And so there's this startup reaction here that ensures that the initialization occurs exactly once by setting this static global variable to signal to the other reactions, to the other reactors, the other instances that are using the IMU, that the initialization has occurred. It also defines a common set of outputs for the gyroscope and the accelerometer, which extends the same base class. Okay, so the gyro component and the accelerometer extend the same base class. They inherit the same initialization code, but they do something slightly different. This is using some of the these are SDK libraries that are provided by Polulu as part of the robot distribution, right? To read gyroscope data into a data structure and then produce it on the outputs. And then this trapezoidal integrator is just doing a simple integration algorithm. It happens to be the trapezoidal method, but that's not that important. Perhaps more interesting is that the state variables, an integrator has to have state variables, and these are marked as reset state variables, which means that if you use this trapezoidal integrator inside of a modal model, and that modal model takes a reset transition, then you will get a resetting of that state variable. So let me show that at work with I'll go back to the simple example since process actuate 2. Here we go. All right, so in mode B, what I'd like to do is instead of just negating the input, I'm going to define a state variable that is a counter, okay, of type integer, initialized to value 1, say, and then what I'll produce on the output will be the value of the count variable. All right. And then again, I will use the input to switch modes. All right. So let's see what the behavior is. Oh, I'm getting a warning here that I have to specify whether the transition to B is a reset transition or a history transition. So let's call it a reset transition. Okay. And then compile this again. And okay, it tells me success. It has compiled it. And let's try to run the right binary this time. Whoops, I forgot to increment to the count variable. Let's do that. Okay, now one of the things that you're going to see is when you re-enter this mode, the state variable gets reinitialized. Okay. I can alternatively specify a history transition, in which case, when I compile this and then run it, the second time we enter this mode, the state variable should pick up from where it left off. All right. So in the robot solution, the fact that the gyro angle uses these trapezoidal integrators that declare these as reset variables means that a gyroscope is essentially measuring angular velocity. Excuse me. In order to measure angle, you have to measure angle relative to some starting point. And what this does is this resets the starting point every time you enter this mode. And for that reason, the robot is able to, when it enters this mode, turn 90 degrees by then just checking the value of the value returned by this gyro angle component against this 90-degree threshold. Okay, that makes sense. Let me show a slightly more interesting robot example. So this one, this particular example is proactive, not reactive. Here's a variant that uses also a modal model, but it has more modes. Okay, it has a driving mode and then a turning mode. So it's going to try to use those to drive in a square as before, but it also is using bump sensors on the robot. And if the left bump sensor triggers, it goes into a mode to back up to the left and then goes back to driving. And if its bump sensor on the right detects a bump, then it will back up to the right. And so if we compile this guy, and I have to reconnect the robot to flash it. Connect it to my USB port, put it in boot select mode. And use the Pico tool to start and execute it. Called robot avoid solution. Okay. And now go back to the floor of this hotel room in Spain. And, oh, shoot. Just dropped the robot. Visible.
I can see it.
So then if I create an obstacle for the robot. These bump sensors are not all that reliable on this robot, but you can see that turning direction depends on reaction to those bump sensors.
Cool.
Okay, so that's emphasizing the point here is, this is running on bare metal. You could create similar programs to run on a Linux-based platform. There would be really very little difference. These would use a different specification in the target. The particular platform that we're calling RP 2040 is a bare metal platform, and the code generator takes care of making sure that all the infrastructure that's needed is there. It's using an unthreaded version of the runtime because there's no thread library here to make use of. And that's what enables it to run on a very simple bare iron machine without much in the way of other support. Okay, so I'd like to just quickly show you a little video of what the students are kind of charged with doing in this embedded lab. Maybe Martin can post in the chat the link to the embedded lab exercises, which are open and available to anybody who wants to use them. But they ultimately program the robot to climb up a ramp and detect that it's reached the top and avoid running off the edge of the ramp and then go back down there. And so there's an instance of a solution
So
to that.
this lab you mentioned is for undergraduate students, right?
Yeah.
Cool.
Yeah. And so.
Did you have to teach them Lingua Franca?
Yes, we do that as part of this. The lab exercises assume no prior background with Lingua Franca.
Okay.
I can show another example. Actually, there's a video that Alex Schultz Rosengarten created that he used to illustrate his model programs. This is a Furuta pendulum problem. So it's a pendulum design that starts out with the pendulum hanging down and then tries to impart energy to the pendulum and then swing it up and then balance it in an inverted pendulum style. You can see that this animation was actually, he generated this animation driven by a Lingua Franca program that was combining a numerical simulation of the pendulum with the controller implemented in Lingua Franca and then a graphics engine to produce the animation. And all of these were done in Lingua Franca. I can show you what his program looks like. So we'll hide all the details here, but there's a pendulum simulation here that takes as a control input and potentially a disturbance input. So you can use this pendulum simulation to inject impulsive disturbances like tapping the pendulum and see how your controller reacts.
You're not yet sharing your screen.
Oh, right. Thank you. Sorry. I do that when I switch back and forth. Did you see the video of the pendulum?
No, we missed it.
Oh dear. All right. Let me start that again. So this is the Furuta pendulum animation that Alex created. Okay. And as I said before, both the simulation the simulation is created in Lingua Franca. The controller is created in Lingua Franca, and the animation engine, the generation of the graphics, is done. Well, it's using a web-based tool, but there's a socket, a WebSocket connection to that web-based tool to generate the animation from the Lingua Franca program as it executes. Okay, so the idea is to first impart energy into the hanging pendulum, then catch it, and then balance it. Okay, and that sequence of actions is represented very nicely. A simple version that's not just printing output data. The other, but it also has a potential for a disturbance input. My machine is telling me my internet connection is unstable, but hopefully this is coming through. So we have this simulation, which then produces simulated sensor data. The pendulum controller itself is at the top level a modal model. And so we see that there are 3 modes of operation. There's a swing up mode, catch mode, and a stabilize mode. And the swing up mode has internally some control behavior that is trying to impart energy onto the robot, and then also detect when the angles are appropriate to switch into the catch mode. So it's using just the angle of the pendulum on the end. When that hits a threshold, it switches into the catch mode, uses a different control law to catch the pendulum. And then when the angle and angular velocity have reached a certain threshold, I guess, I forget actually which angle is the horizontal arm and which angle is the vertical arm. One of these is the horizontal arm, the other one is the vertical arm. Then you switch into a stabilized mode, which has another control law altogether. Now, one of the nice things about this is that you can take this same pendulum controller and drop it into an implementation. So you don't have to redesign that. Okay, this is going to generate C code that can run on a bare iron microcontroller. And so you can replace your simulation component with something that is reading sensors, just like we saw on the Pululu robot, and driving actuators, just like we saw on the Pululu robot. And then just drop in exactly the same controller that you used in simulation, and you're not switching in the usual model-based design way where you build a model first and then you throw it over the wall to someone who implements it. In this case, the implementation is the model. You're using the same code for both the implementation and the deployment of the program. And that's one of the really primary objectives of the Lingua Franca framework. Okay, so the next thing that I would like to show you is rather different but very powerful capability in Lingua Franca, which is the ability to create federated programs. And let me try not to make the same mistake. I am going to copy and this into a new, the simple sense process actuate into a new program. And so if I try to run the wrong program again, please tell me. All right, we're now in sense process actuate 3. So let me make a 1-line change to this program, which is simply replace the word main with federated. Okay, the graphics changes very slightly. I get a little cloud here. All right, but other than that, everything looks just the same. When I compile this program, however, things happen that are really quite a bit different. All right, but make sure, yes, it looks like it is compiling the 3 version. We go to the terminal and let's look at what we got. All right, so first, if I look in the bin directory, there is a sense process actuate 3. All right, there it is. I can run it just like I did before. And it will do pretty much the same thing as the original program. All right, but there's a really quite a significant difference in what it's doing currently. Okay, so let me show you that, first of all, this program that I just executed isn't actually a binary, it's a script. Okay, so if I go to the bin directory, that's it, and open sense process actuate 3, I find that it's actually a bash script. And in this bash script, it actually launches 3 programs right here, okay, plus a coordinator that we call the RTI. If I go and I look in the directories that were created, there is a new subdirectory called fedgen, which has a sense process actuate 3 subdirectory. And within that subdirectory, there's its own bin directory, which has now 3 binaries, 1 for each federate. All right, so what happened was, looking at the diagram again, whoops, the diagram, I have to be there, yeah. Each top-level reactor gets translated into its own standalone program, and that program includes the communication and coordination between each of the components. Okay, so these are now going to execute as separate programs. They can be mapped onto different machines. Okay, I can specify, for example, that I would like the coordinator to run on a particular machine by saying, say, wessel.eecs.berkeley.edu. And if I have SSH access to that machine, then the script that will be generated will automatically handle deploying the coordinator on that machine. Berkeley has actually turned off SSH access from outside the campus, so I would have to have a VPN connection right now to be able to run this with the coordinator on Wessel, so I'm not going to do that. The other thing that you can do, though, is you can Dockerize each of these components. So you can put the coordinator in a Docker component and each of the federates in a Docker component, and then deploy those within Docker on containers that can be then put into the cloud. Okay, so there's instructions for doing that on our website that you can find. But what I'd like to do now is modify this program a bit to highlight a few of the really interesting features of Lingua Franca. So in particular, let me change the actuator here so that the actuator has a second input. So let's call the second input int2 of type int. And it has some reaction, reaction to int2. And this will, for this test case, again, just, second input. So now it's got a second input. Now, suppose that I create a second sensor. All right, and for this illustration, I'll just use another instance of the same sensor, but it could be a completely different sensor. That would actually be more useful, probably. And now I can connect that second sensor to the second input of the actuator. All right. Now I want to emphasize something rather important about Lingua Franca that you won't see, I think, in other frameworks in quite such a clean way. In this particular case, these two sensors are instances of the same sensor, and consequently, they have the same timer, okay, which means that they are producing outputs that are logically simultaneous. In a completely asynchronous framework, there might be a race condition on what the actuator sees. It's quite possible that it might see the output from this sensor here before it sees the output from this sensor because of the time it takes to do the processing. But Lingua Franca prohibits that. It has a deterministic semantics, and because the processing is logically instantaneous, the output from the processor is this signal produced by the processing is logically simultaneous with the output from this sensor, and Lingua Franca guarantees that the actuator will see these two inputs simultaneously. All right, so this actually eliminates the particular kind of race condition that that Martin was showing right at the beginning of this session in AutoSAR, where the sensor data was getting misaligned because of this inability to have this logical simultaneity. Now, the logical simultaneity can get much more subtle. So, for example, I could specify that the sensor could have a parameter that is its period. It has value time, and maybe the default is 500 milliseconds. And then I specify that the period is as so, but now the second sensor, I'm going to change the period to say 1 second. All right. And now what's going to happen is that every other output from the sensor here will be seen by the actuator alone, and only this reaction will be invoked. And then when the two outputs of the two sensors align, in the actuator will see both inputs, and consequently both reactions will be invoked. And that's guaranteed by the framework. All right. Now, Martin briefly mentioned this result that we have, which to me is one of the most interesting things to have come out of the Lingua Franca project, which was this realization that we call the Cal theorem. So this idea that the actuator sees these two inputs simultaneously when their logical times are identical is a property that we call consistency. And it means that what the actuator sees is consistent with what any other observer of these two sensors would see. If I route these two outputs to anything else, okay, in the component, even if it's running on a different machine somewhere halfway around the world, communicating over networks, that other component, so if I create another actuator, right, so let's go ahead and do this. A2 is a new actuate. All right, and I connect that up to get the same inputs. So let's make use of copy and paste here. All right, I can map these two actuators to two different places in the world, and they will have a consistent view of the state of the world, because the two sensors, when they produce outputs that are timestamped the same, are guaranteed to be provided simultaneously, not just to this one actuator, but to both actuators. And consequently, the view that they have is consistent. Okay, this is a form of consistency that we call strong consistency. The Cal theorem, which is a generalization of Eric Brewer's CAP theorem, tells us that there's a price that you pay for this consistency, and that price is absolutely fundamental and unavoidable. And it's a price in availability. What it means is you can see it quite intuitively. Suppose that this processing takes a long time to execute. Okay, then what's going to happen? Well, the invocation of this reaction to this second input may have to be delayed to wait for the results of the processing. Okay, in Lingua Franca and in general, in fact, this component is not guaranteed to produce an output, and you may not know whether it produces an output until it's finished with its processing. Okay, so as a consequence, in order to preserve this determinism, in order to preserve this strong consistency, you may have to wait some amount of time, which is dependent on not just the processing time that it takes here, but also the communication time. If these components are scattered around the globe, the communication time could be quite substantial. And so there's a loss of availability in that this component cannot react immediately to this sensor because we're insisting on strong consistency. So we lose availability because of the requirement for strong consistency. So the Cal theorem tells you that that trade-off is absolutely unavoidable in distributed systems. The Cal theorem, the CAL are consistency, availability, and latency, where the latency in this case is due to network communication and processing times. Okay, so in MSoft next week, we are presenting a paper on the Cal theorem, and I invite you to come listen to that paper, and we can give you quite a bit more details about it at that point. But it's a fundamental trade-off. Now, one of the interesting things about Lingua Franca is that you can actually explicitly work with this trade-off. So in particular, I can manipulate timestamps. So for example, I can say, well, I can say that this communication will occur with a 100 millisecond offset in the timestamp. And what this does is this relaxes consistency, allowing for, in exchange for which I get better availability. So what happens now is that for the actuator to react to this second input, it has to wait for this processing and communication time minus 100 milliseconds. So if the processing and communication time is less than 100 milliseconds, then the actuator doesn't have to wait at all, and it can process this sense input immediately, which means that we gained availability at the expense of consistency. So Lingua Franca gives you an explicit way to work with this very fundamental trade-off and to build programs that take it into account. So with that, we're at the top of the hour. I think it's time to close this, but I guess we can take a couple of questions if anyone has questions. Okay, well, let's declare success. I think the recording of this will be available together with my stumbles on running the wrong binary. But that's life. That's what happens when you do stuff live instead of in PowerPoint. All right, thank you very much.
Thank you. So yeah,
Thank you.
thank you so much for this great session. It was quite, impressive to me because, in addition to its research value, what was quite impressive to me was its educational value. So again, let me turn on my camera. So what I experienced in my class, I work for Santa Clara University. We put a lot of emphasis in, teaching and education. So when I teach, this real-time embedded system, even in this real-time embedded system, people, ignore this timing guaranteedness because, if you look at the gap between practice and theory, we are trying to teach, this timing guaranteedness and real-time scheduling. But what you see in practice is that even the most popular real-time operating system ignore EDF, right? And they don't care about this, timing guaranteedness. And as Martin, presented at the beginning, even this most advanced, automotive programming platform has this timing uncertainty, and people live with it, and people believe that it is okay to have this kind of uncertainty. And so it's like this, it is extremely difficult for me as an instructor to, persuade the importance of this timing behavior of the system. So from this point of view, I found it extremely helpful to teach this, timing things with some interesting example. So
Yeah.
I have a lot of curiosity about your course in the merit system, because do you go by quarter or do you go by semester at UC Berkeley? Do you have enough time to teach Lingua Franca in your class?
Yeah, it's a semester length course that we have, but the lab exercises are meant to take only the first half of the semester. So I think it would actually be completely compatible with a quarter based course. The reason for that is that we have the students then do projects in the second half of the semester. And one of the goals of the course is to actually integrate the design process with the modeling. So, for example, in the course, we have an introduction to formal methods that uses state machine-based technologies. And for that reason, this modal model capability that Alex Schultz-Rosengarten created has proved incredibly valuable, because the students now see the state machines not just as a theory, but also as a way to build code and to build understandable and analyzable code.
Right.
Yeah. So, okay. Well, thank you very much. And we'll call it here.
Sure. So, as I said in the email, I will download the file and will share it with you as soon as possible.
Great.
Great. Thank you.
Great, thank you.
Bye.
Bye.
Bye-bye.
Thank you, everyone.